We interact with matter literally every single second of our lives. Whether it's the air we're breathing right now or the chair you're sitting on, it's just everywhere. But what if I told you that deep, deep down inside the most basic building blocks of all that matter, there's a physical secret hiding? A secret so mind-bending that it completely shatters our everyday understanding of reality. Well, buckle up, because today we're diving headfirst into the deepest, heaviest mystery of the microscopic world.
So, right smack in the middle of every single atom in the universe is its nucleus. Now, we usually picture atoms as these tiny, solid little building blocks, right? But the truth is, an atom is almost entirely empty space. The vast, vast majority of its mass, the actual stuff that gives any object its weight, is completely crammed into that tiny central core. And listen, we aren't talking about the density of heavy metals like lead or gold here. No way. We're talking about numbers that literally break the boundaries of basic math.
Just try to wrap your head around this for a second. 10 to the power of 17 kilograms per cubic meter. Okay, let me put that into perspective for you. Imagine you take a box that's 1 meter by 1 meter, so roughly the size of a standard washing machine. Now, if you were to fill that washing machine entirely with raw nuclear matter, it would weigh 10 to the power of 17 kilograms. That is essentially like taking a massive mountain range or a huge chunk of the Earth's crust and crushing it down with such terrifying force that it fits perfectly inside your laundry room. It's just absolutely wild. The density of nuclear matter is so high, it's actually kind of scary to think about.
Now, academic physics textbooks are usually, well, pretty dry, right? They're objective, they're strictly scientific, they definitely don't just throw around exclamation points for fun. But check this out. When we calculate nuclear density in grams per cubic centimeter, it comes out to the order of 10 to the 14th power. That number is so staggeringly huge that even the textbook author was blown away. The magnitude of this math is so intense that a strict academic author literally had to break character and use an exclamation point just to show their sheer amazement. Honestly, I think that's such a beautiful, relatable human reaction to a crazy scientific fact.
Okay, so how does this actually work? How on earth can so much mass be packed into such a tiny, microscopic space without instantly collapsing into a black hole? Well, the basic rule of density is pretty straightforward, right? It's just mass divided by volume. Simply put, it's how much stuff is stuffed into a certain amount of space. So, to really understand nuclear density, we need to measure the mass of the nucleons, that's the protons and neutrons bound together, and then measure the incredibly tiny volume they're squeezed into. It's like a giant, fascinating analytical puzzle.
To solve this puzzle, let's look at the radius of the nucleus. It has a constant base value that we call R0, and it equals 1.2 femtometers. Now, what exactly is a femtometer? It is 1 quadrillionth of a meter. 1 quadrillionth! We are talking about an arena so exceptionally small, it's almost impossible to visualize. But within this unfathomably microscopic volume, all of that massive nuclear weight is just absolutely packed in, shoulder to shoulder.
And right here is where the ultimate secret of atomic physics reveals itself. You see, the mass of any nucleus is independently proportional to A. In physics, A stands for the mass number, which is just the total count of protons and neutrons. More protons and neutrons naturally means more mass. Makes sense, right? But on the flip side, the volume of the nucleus is also completely proportional to this exact same A. So as you add more protons and neutrons, the spherical volume of the nucleus expands at the exact same rate. Mass and volume are stepping completely in sync, hand in hand, both being perfectly controlled by that mass number A.
Which brings us to a highly counterintuitive rule of nature. In our normal, everyday macroscopic world, when you clump things together, their density can change based on how tightly you pack them. Think about making a snowball, right? You can lightly pack some snow together, or you can really squeeze it hard to make a heavy, super dense ice ball. But atoms? They do not play by those rules. The laws of quantum mechanics and the strong nuclear force are incredibly strict. They dictate exactly how these particles bind to each other, and there is absolutely zero room for negotiation.
So, when the mass grows with A, and the volume also grows with A, guess what happens in the density equation? The A on the top completely cancels out the A on the bottom. Meaning, nuclear density does not depend on A at all. Whether you're looking at a tiny, lightweight helium atom with just a few protons and neutrons, or a massive, heavy-duty uranium atom loaded with hundreds of nucleons, the density of their nuclei is exactly the same. It is a constant, universal rule for all atomic nuclei, regardless of their size or weight. How crazy is that?
So, let me leave you with this thought. If the density of every single atomic nucleus in the entire universe is exactly the same, could massive celestial bodies like stars be made of this very same tightly packed matter? The answer is yes. When massive stars die and collapse under their own crushing gravity, they literally squeeze out all the empty space inside their atoms. What's left behind is essentially a giant ball of tightly packed nuclei. We call them neutron stars, objects with the exact same incomprehensible density of 10 to the power of 17 kilograms per cubic meter. The tiny, microscopic physics of the atom perfectly mirrors the massive, sweeping physics of the cosmos. And honestly, looking at the universe that way, it changes absolutely